Thank you very much, Bruno, for your kind introduction. Good morning, everyone. Can you hear me well at the back? Thank you. So I know it's quite tough to be here at this early morning, including myself. So thank you for making your effort for this. So I'm going to share with you some of my view about the relationship between two disciplines. You might wonder what it means exactly by putting two MLs in the title, but Bruno told me, no worries, people can tell the answer from the French version. So now you might wonder, so basically here I meant to put ML as a sort of latent variables, which I think statisticians always like to talk about it. So instead, ML represents basically the cornerstone topic, maximum likelihood, and for machine learning, which plays a big role in AI. And so now I need to be familiar with it. Okay. And historically, these two disciplines have developed sort of differently, but they share a common mission, extracting information from data. So data would connect both disciplines here. And I'm going to give you a very quick, brief introduction to compare both disciplines here. And definitely my intention here is not really to draw a clear boundary between both fields, but I just want to make a quick comparison so we can see their complementary strengths. A natural question is, what is machine learning? And surprisingly, there is no universal definition for that. For example, according to Wikipedia, machine learning, the term was introduced by Arthur Samuel in 1959. So this is basically a discipline that studies statistical algorithms that can learn from data and generalize to unseen data. And the typical task will be implemented without explicit programming language instructions. And another definition according to the Foundation of Machine Learning Research Monograph, those authors define machine learning as sort of a collection of computational methods, which focus on data representation and predictions. And we want to do accurate performance. On the other hand, according to a deep learning book by Goodfellow and his colleagues, they describe machine learning essentially as a form of applied statistics with increased emphasis on using computers, but decreased emphasis on constructing confidence interval or doing hypothesis testing. So one important thing here is machine learning methods are fundamentally related to statistics. And the difference between two disciplines basically are reflected in terms of their emphasis, skills, and computational strategies. And there is no clear boundaries between these two disciplines. So here I'm going to give you a very quick oversimplified analogies to see their differences. If you think about cooking, so what would you do when you first do your cooking when you were young? Are you going to follow some recipes, or you are going to do your own experiment? So if you think of this setting, then statistics is pretty much like a cooking with a recipe, which means we follow prescribed steps and we know what gradients and how much amount would be used. On the other hand, machine learning is more like cooking without a recipe. So we don't even know what ingredients would be and the amount would be and what the cooking steps. So we would do our own experiment many times until we make a good dishes. And when we become an experienced cook, maybe we want to create our own new dishes. So in that sense, you might need to combine both methods. And another quick analogy is about language learning. So when we learn our mother tongue, and we know for little baby, infants, they don't know any grammars. They don't know vocabularies, right? So the basic way they learn language is try to mimic what they received or what they heard from the surroundings. And based on large feedback and extensive interactions with maybe mom, dad, or anybody around their babies, then they gradually learn how to speak. On the other hand, statistics is sort of like learning in school. So in that case, we would learn grammar rules, vocabularies, and understand the writing structures and gradually build our own writing skills. And if we want to learn a new language when we are adult, or maybe when we are young, what would we do? Then you might use two typical approaches, just simply mimicking pronunciations or sounds, and also learn textbooks so that we can combine both approaches. And now a central question is, what would unify both fields? So in that sense, we could, oops, sorry. I forgot to, because I have my laptop here. Now, what would be the key theme that unify both fields? How do we learn from data and generalize beyond it? So in this sense, we can see statistical science and machine learning sort of have a different emphasis, and the workflows are slightly different. So if I'm going to make a quick comparison here. Okay. So basically, the primary emphasis for two disciplines are different. Instead, we focus on inference and uncertainty quantifications, and machine learning focus more on prediction and large-scale learning. And in terms of the data structures, statistical science often deal with numerical data. And for machine learning context, data could be basically digital. And in terms of the parameter scales, and in statistical science, normally our parameter dimension is small to moderate. And for machine learning context, it could be huge. And also in terms of the sample size, and usually our sample size in statistical analysis is could be small, like small sample analysis. We could deal with sample size on the scale of tens, or we could deal with something around maybe 10 to 5. And in machine learning context, many times we deal with large to massive data set. And in terms of the scope and primary emphasis in statistics, we work within either frequentist or Bayesian framework with different modeling strategies, including parametric, semi-parametric, or non-parametric approach. And machine learning field focus on different task learning that could be divided in terms of supervised, semi-supervised, and unsupervised learning, and reinforcement learning. And in terms of the complexity, in statistical analysis, we often focus on complexities in terms of the model and the data themselves. On the other hand, in machine learning, we would further look at computational complexity and storage memories. And in statistics, we emphasize model identifiability, and this may not be explicitly imposed in machine learning field. And so in terms of the interpretability, and often we would think in statistical modeling, we have a high interpretability, and in machine learning models, many times it could be no. And these two fields do share something in common. We all use X and Y to represent our variables, differentiate them by their nature. On the other hand, we use different terminologies. In statistics, we often call X as covariates, predictors, or explanatory variables. And in machine learning, we call it input, feature, and instance. And for Y, we call it like response, outcome, dependent variables. In machine learning, we often call it output or label. And another thing is, when we develop a new method in each field, how would we know it's useful or valid? So in terms of the justification of validity of individual approach, we also have different emphasis. So if you think we have like x-axis represents a sample size scale, and y-axis represents different collections of different methods, in statistics, traditionally we emphasize discussing asymptotic results for a newly developed method. So in that case, we put ourselves in a hypothetical framework by considering sample size n approach infinity. And we evaluate a given method is meaningful or not. On the other hand, for machine learning context, we pretty much work on individual benchmark data sets with a given finite sample size. So in that case, it's more like we look at different approaches by looking at the vertical axis here. And of course, you would notice in machine learning context, usually the data size is enormous, which means our n is actually huge, pretty much close to infinity in practical meaning. So in this sense, the differences between these two perspectives may not appear as large as they are. But of course, in this two intersection part, we also need to consider about the increasing model complexity. In a sense, right now in both fields, we do talk about the settings and parameter dimension P approach infinity or divergent. And this is a very active area which may have many subtle new results here. And so basically, statistical science and machine learning are linked by dealing with data, and we have a different emphasis. And when we develop new approaches, what do? Usually we have implicit assumptions. Our data are perfect, in a sense, no error. Naturally, we may ask, what if this assumption is not true? What do? So in both fields, we have quite many different research approaches. We do have different terminologies. In statistical science, we call this is a measurement error problems. In machine learning context, usually people would say this is noisy data. And we also differentiate measurement error arise from either X, which would call covariate measurement error in statistics, and input error in machine learning. And if we have an error in response in Y, then in statistical field we call response error. And in machine learning, we usually just call it label noise. Now I'm going to give you some quick examples to illustrate measurement error or label noise problems. So in statistical field, there are quite many different reasons related to measurement error. It could be related to data collection process, or it could be driven by the nature of the variables. For example, in survey context, measurement error is a common concern. Reporting error would be typical, especially when respondents need to answer the sensitive questions. So in this, in this example, this author found about 10% of respondents will over-report their salary. And this happened to people whose salary distribution tended to be low. And there was a greater measurement error in men than women. And the relationship between true income and reported income would be displaying a nonlinear relationship for men, but a linear relationship for women. And in this case, we can't really treat this difference as a white noise because it depends on gender, also depends on the true income. Another issue is related to the variables itself. For example, if I imagine in our model, our variable represents a long-term average for certain quantity, like blood pressure, cholesterol level. And for those kind of variables, there are two typical errors, either reading errors or biological. So I think, biological variabilities. So sometime last year when I was given these examples, audience showed disbelief about biological variability in blood pressure. So then I decided to collect data for myself. So this graph represents my own blood pressure information over 8 weeks. Last year, starting November, November 1st, something like that. So you can see there's a huge variabilities. And the blue and green stripes indicate the normal range for systolic or diastolic blood pressure. And especially if you look at the first 2 weeks, my blood pressure tends to be very abnormal. So one of the highest point is even higher than 150. So that really alerted me. Then I just keep measuring my blood pressure almost on a daily basis, but at different time points. Then for the following 6 weeks, it seems my blood pressure becomes normal. So I feel kind of relieved. What's the reason for these very different patterns? The reason was for the first 2 weeks, that was a rebuttal period for a machine learning conference. So I have to meet the deadline. Pretty much had 2 consecutive all-nighters. I only slept maybe a few hours when I was really tired. So this simply indicates our blood pressure could highly fluctuated according to our work routine or busy schedules. And of course, for like epidemiology studies, measurement error is also a typical concern. Many times, some variables cannot be measured precisely. It's impossible. For example, if you think of like a body composition and dietary intakes, those kind of variables, we don't have a way to measure them precisely. So we can only use some surrogate measurements to replace it. In this case, addressing the discrepancies between the true variables, which is always unknown, and the concrete measurements is very important. Now, a natural question is, Does that mean if I have data with measurement error, are they useful? Can we do something about it? The answer is yes, if we address the associated issues carefully. And there are quite many research books and many research papers in this field. And I think there's a, okay. So this is kind of maybe device error, display error. Okay, I can't flip. Okay, let's look at the French version. So I also wrote a book about measurement error focusing on issues in biostatistics, and also co-edit a handbook with Aurora Denego and Paul Gustafsson. And also in machine learning field, this is a well-recognized issues and which are documented in these books. And I'm going to give you quick examples in machine learning field. For many benchmark data sets, they contain noise or label noise. And for example, in image recognition and text classifications, this is a typical concerns. And they may have a different sources of generating label noise, and depending on if it's image data or text data. And medical imaging present somewhat most challenging label noise problems. One key challenge is that medical image would be labeled by radiologists, which definitely is time-consuming and very expensive. This motivated researchers, especially the machine learning researchers, to develop some automatic algorithms to do labelings. For example, if we look at this data set, this is a large-scale chest X-ray data set, which contained over 100,000 images. That would be automatically labeled by using natural language processing procedures to extract individual disease labels. And this is a fast, but definitely there would be associated issues here. So unfortunately, I don't read French, so I need to rely on this side. There would be a typical error generated by natural language processing procedures here. And also there would be inherent difficulties in terms of variabilities from reading or interpreting individual graphs here. Then you might wonder how serious is this problem would be. And there are quite many studies in the literature, and one paper they estimate in the whole world about 8.5% of data include label noise. And in terms of brain tumor segmentations, those authors estimate about 74 to 85% of variabilities among those inter-reader differences. Now the next question is, what do we do? How to address label noise issues? So here I'm going to give some quick examples based on the research with my collaborators. The first application is about medical imaging here. And we have about over 1,000 image here, which would be labeled by about 1 to 21 individual readers on a scale from 0 to 3. And the proxy ground truth here is determined by consensus. And turned out mislabeling rates are quite substantial here, about 21% of mislabeling for normal cases and 42% for abnormal cases. And our goal here is to develop methods to address these issues by combining statistical thinking and machine learning tools. We typically use deep neural networks to learn image representations, and then use a statistical inference approach to accommodate associated variabilities. And the second example is about label noise in single cell data. And the data involves thousands of genes across hundreds of thousands of cells. And the goal here is try to identify cell types and states. But the challenge here is there is no reliable ground truth. And the manual and annotations involve subjective and expertise-dependent errors. And using automatic generated algorithms to do labeling will give us different labels or even different number of clusters. So the key idea here is we want to treat those automatic algorithm-generated labels as sort of crowdsourced annotations. And we want to use statistical methods to address these issues here. And we use deep neural network again to introduce flexible architectures to model the true labels and annotated labels. And then we develop conformal predictions to do inference here. Now I'm going to look at another problems related to supervised learning, which means each data point has an individual label. And in image classification or speech recognitions, if we want to receive accurate labels, it will be very time consuming. So in this sense, what do we do? For example, if you look at this graph, which is related to self-driving car research, then for any given image, we want to distinguish different objects on the image by label them. Say differentiate like a traffic light, pedestrians, vehicles, or even road conditions. If we want to do that, definitely by a human, it will be very time consuming. So a practical way is use crowdsourcing techniques. So what do we mean by that? That basically means we just use the information or contributions or opinions contributed from people worldwide via internet. So this is a quick way to give us labeling information. For example, for Amazon Mechanical Turk platform, it can obtain hundreds of thousands of labels within just a few hours, and each label is very cheap, just costs a few cents. So this gives us a quick way, but of course we can see there's a practical issues. Different people have different skills, so that will induce unavoidable large noise in our labels here. Now the question is how to address it. Here I'm going to look at one of our research papers on these topics. So this is a joint work with my current PhD student Hui Guo and colleague Boyue Wang in computer science department. And we just put ourselves in this abstract framework. So I have a feature, which means covariates X. And I also have a finite number of different labels denoted by label space. And for each item, we can observe input information. But for the output Y, I don't observe it precisely. Instead, we have multiple annotated informations for each given subject. So I'm using YI tilde, superscript 1, 2, 3 until R to represent those labels obtained by crowdsourcing techniques. So in this case, our ground truth YI is unavailable, but we have repeated measurements YI tilde, which could be identical or different from our true label. So our goal here is try to use the noisy labels to train a classifier which can do prediction for future input. Then what would we do? First, we just introduce simplified assumptions, assuming all those R annotators will do annotations independently. And of course, this assumption is not really critical, but just for simplicity, I look at these scenarios. With these assumptions, then based on our repeated annotated value yi tilde, we can easily rewrite this joint distribution in terms of the product of conditional distribution for each labeled value yr tilde given x. And we can further use a probability product rule to decompose this into two conditional probabilities. So the red part is called transition probability or matrix. Sometimes we call it confusion matrix. And the blue part we call it base model. And the red part indicates the relationship between the true label y and annotated Lois label yi tilde. And the blue part is something we want to learn in order to build our classifiers. So in the literature, people often make these instance independent assumptions, which means conditional distribution of yi tilde given y and x will not depend on input x at all. So that can significantly simplify the discussions and avoid under these non-identifiability issues. But of course, this has a price to pay. In a sense, it's very restrictive. So we want to renege this assumption by coming up with instance-dependent transition matrix. So our goal here is we try to incorporate two characteristics related to annotation process to reflect different effects from different annotators and possibly the dependence on the underneath two class labels. Then what would we do? So we only need to use a statistical thinking to introduce a conditional probability of yi tilde given true y and x. So we use a simplest way, a linear combination of two functions, psi1x and psi2x, to show the dependence on input x. On the other hand, we think this could depend on which annotator is doing labeling process and what is the underneath truth. So we also attach two weights, A and B, depending on either annotator information or true class label B. And those weights would be unknown. And also our psi1, psi2 functions are unknown. And we just link them by add them up. And of course, this can't really give us valid probabilities. So we further apply G function, so-called soft max functions, to make this legitimate probability, taking value between 0 and 1. So this is a basic idea. Now the next step is, what is psi1 and psi2 functions? How would we specify that? And of course, we can use traditional ways, say, make it as a linear function or quadratic function or whatever function we like. But here, instead of doing that, we just take advantage of deep neural network architectures. Trying to think psi1, psi2 as any unknown, maybe nonlinear mathematical functions, then we have a p-dimensional input here. Then I want my output expression represent these psi1, psi2 functions. What do? Then we just introduce a sequence of different hidden layers, and within each layer we may have different numbers of nodes. Then all those adjacent layers, their nodes would be linked. So we use this forward, so-called forward deep neural network to express these unknown functions. So mathematically, this expression simply means in my first step, I start with my x p-dimensional function, then I attach unknown coefficients, weight, and intercept. In machine learning, we call this bias. So we start with this linear function to link this nodes within these two adjacent nodes, and then apply an activation function, usually user specified. Once we get the output for the first hidden layer, then we repeat, move to the next hidden layer. So we do this recursively. Then mathematically, we can just use a sequence of linear functions in combination with the activation function. Then we can approximate any unknown function here. So this is a basic idea of deep neural networks. Now the next question you might wonder, is this really necessary to consider all possible links among nodes within adjacent hidden layers? So in this case, we think maybe for some situations, we don't really have to use a fully saturated deep neural network. Then we think maybe some nodes do not have to be connected. So to reflect this, then we just introduce indicator function gamma to indicate some nodes may not need to be connected here. And then we also want to put ourselves in this framework that maybe we might have some prior informations. To reflect that, then we just assume our prior distributions for deep neural network parameters given these indicator functions will follow certain mixture distributions. And then for those associated weights, associated indicator gamma, we just assume it has some Bernoulli distributions. So this is the whole idea of trying to put this deep neural network in Bayesian framework to sort of reflect we might have prior information here. So with this model setup ready, now what would we do next? So we want to study or estimate associated parameters. So the key idea here is to look at general instance-dependent transition models. Then we are going to utilize this notion, so-called anchor points. So what do we mean by anchor points? The basic definition means for certain covariates x, it is so unique in a sense, if I know x, then the corresponding label value y equals to k will be happening with probability 1. So in this case, that basically means anchor points would be uniquely determine the label information. Why do I need that? Because for those special covariates, then we can quickly derive this identity, which means using observed data annotated y and true covariates, then we can link our, we can express our confusion or transition probability here. So the question becomes, if I'm able to find anchor points, then things would become easy. So now I assume I'm able to find my anchor points based on my observed input x and annotated value y tilde. If x is anchor point, then the label y will be automatically determined. So this is the whole idea of trying to find anchor points. Then the next question is, what do we do? How do we find anchor points? So here we are going to use the procedures in machine learning context by using majority voting procedures to determine anchor points. And those papers give us like empirical ad hoc procedures. And in our recent papers, we also carefully identified associated conditions to make these majority voting techniques work. And once we can find anchor points, then the next part is I'm going to just combine with my previous Bayesian deep neural network structures and work out posterior distributions, then maximize it and estimate associated parameters. Once this is ready, now we can work out this conditional probability. I'm going to use f theta to represent this learning outcome here. Once this is ready, then we can easily work out the posterior distributions by using standard statistical techniques. Now, the question is this procedure really works? theoretically. So we also identified regularity conditions, and we can say the estimated or learned representation of deep neural network for our transition matrix will be close to the true conditional probability in such a sense. And this gives us, so here we particularly use Henninger distance to describe the discrepancies between two distributions. And this result also extended available results in the literature, which in a sense, traditionally we assume IID assumptions, and in our case, we still require independence assumptions, but we renex identical distribution requirement. So once this has been learned, what is remember my final objective here? I want to do prediction, right? So now here we want to come up with a predicting approach with label noise effects accommodated here. So what would we do here? So basically in here, that means my objective is for my future input, X, which also may be associated with a sequence of noisy annotated values. I want to predict its true underlying label denoted by K star, which will maximize this. Then we convert these problems into two steps. So first, we just rewrite these expressions by combining with our posterior distributions. So this here, H represents a prior information for individual class, and this tau part represents the confusion matrix we have learned by using deep neural network structures. So once this is done, then our next step is I want to find this maximizer K star. Instead of directly to maximize it, we just convert this as a comparison with any other labels. We try to look at pairwise comparisons. And the reason of doing that is I want to sort of use our available statistical techniques. So this will let us convert our problems into a hypothesis testing problems by comparing two conditional distributions, which is related to this conditional distribution with true label K versus alternative K prime. So once we formulate our problems like that, then the remaining is straightforward by using available statistical techniques such as like Lehman-Pearson lemma. Then we can work out the posterior likelihood to do this ratio compared with certain threshold value omega here. So this is the whole idea about constructing our classifier here. Then the next question would be, would this procedure really meaningful or theoretically guaranteed? So we further study its associated bound for Bayesian risk here. Here I use D bar represents those instances with estimated labels we learned from our previous procedures, and Y would be our true labels. I want to describe the discrepancies between our estimated label Y bar and the true label. So we use 0, 1 loss functions to indicate their discrepancies. And then we further attach the prior informations by looking at this expectation here, and we call this as a Bayesian risk. And we want to say how large or how small this Bayesian risk could be. So under certain regularity conditions, we can establish this Bayesian risk cannot be really small. It will be lower bounded by something, and this term will be positive. So this indicates no matter how good you learn your procedures, you can never have a perfect learning. On the other hand, this procedure is also useful in a sense the risk won't be infinitely large. It is upper bounded by these quantities here. And in our development here, this result applies to arbitrary priors. And these upper bounds indicates the dependence on the information from our annotators' skills, and also it involves the under these two labels informations. So here I'm going to quickly wrap this part up by giving you a quick numerical studies. We considered several benchmark data set. In the first two data sets, CIFA-10N and LabelMe, we do have human annotated informations. And for the other three data sets, we have synthetic annotations, so which means we can artificially introduce different rates of annotated errors. So we consider three cases, 20, 35, and 50%. And we applied our approaches to those 5 benchmark data sets and compare with 15 different approaches. So in the first approach, we just look at the case with clean data without using label noise information. And the third approach is one of the earliest approach on dealing with label noise in machine learning context. But the actual approach is based on EM algorithm techniques. And we also compare with many new techniques in machine learning field. So here I'm going to show you 2 quick tables here, graphs here. So for the top panel, that represents the empirical results on CIFA-10 about average accuracies. So that basically means the higher, the better. And our methods produce the topest curve. And the bottom part represents the average estimation error for our translation matrix. So in this case, the lower, the better. And for these 2 cases, if we have moderate or high annotation errors, then our approach performs the best. But when we have a small annotation errors, and when the number of annotators are small, and one approach beats our method, but when number of annotators increase, then our approach becomes better as well. So this simply gives us some quick example how to deal with label noise in concrete settings. Now I'm going to come back to my initial theme from ML to ML. So what do I mean by that? So here, these 2 L's simply means, as I mentioned earlier, machine learning and maximum likelihood, generally representing statistical science and AI. So those 2 fields are not just connected. They actually feed each other. Why? I'm going to give you some quick illustration here. And first, I want to say from ML to ML, from maximum likelihood to machine learning. So we can see there are quite many examples to show invisible victories of statistical thinking or statistical science. This is a quick timetable which highlights the evolution of machine learning. And it begins with Alan Turing's foundational questions. In 1950, he asked, can machines think? So from there, the perception in the late 50 and 60, and the decision trees and propagations in the 80s, and convolution neural network and support vector machines in 90s, and deep learning revolutions in about 2010s. Until nowadays, transformers, generative AIs. So at each step of those journey, statistical principles and ideas play an important role quietly, and they remain deeply embedded in the methodology of machine learning. So here I'm going to give you 2 quick examples. And AlexNet landmark success in the 2012 image computation, and AlphaGo AlphaGo's defeat of world champion Lee Sedol in 2016. Then in both cases, statistical thinking plays a critical role through different techniques such as likelihood principles, Monte Carlo estimations, stochastic approximations. So those are invisible victories of statistics within machine learning field. And another example is related to natural language processing. So this is a quick arena that shows why statistics is central. So natural language model could be fundamentally related to statistics in a sense. We can treat this as just statistical problems. For example, if we are given this partial sentence, the dog ran, what would be the next word? Then you might say, okay, using like a semantic or grammar rules, it could be ran away, ran happily, wild, or run around. So what do we do? How do we know the next word? So essentially, this is a statistical problems. Given current context, what's the probability of the next word? And to do that, so we can use statistical estimation techniques to learn conditional probability based on whatever data we have. And then we would choose the next likely word or sentence to do maybe even translations here. And to show these procedures, so first we need to convert this raw text into something numerical, because raw text cannot be directly usable for machine or even for statistical analysis. So in this case, we would divide the whole sentence into smaller parts by so-called tokenizations. So a quick way is just use individual words, but in large language models, people actually just make a token, could be a small word or part of the word or just some characteristics. And in this case, we would convert each single unit into a sequence of numerical values. And so we just use this sort of like a binary data, so-called one-hot vectors, to represent individual words. And then this numerical representation would allow us to use statistical techniques to do analysis or estimations. So this whole process involves, excuse me, involves like four procedures: how to convert raw data, how to represent it, and then to do predictions. And so traditionally, n-gram models is one of the earliest language models, which means I'm going to deal with a sequence of words or tokens. Then instead of directly study this, we use a product rule to convert this as a sequence of conditional probabilities. And once we use these formulations, then maximum likelihood estimation ideas could be used. And we could also introduce some additional ways to say, maybe do some smoothing to avoid some conditional probabilities to be zero. And we could also introduce some like embedding techniques to reduce or to introduce sparsity here. So in this case, we are dealing with a sequence of words sequentially. And nowadays, for large language models, we may introduce more advanced techniques to try to incorporate a spatial relationship. So instead of just looking at those words in a forward way, sequentially, maybe we can even look them backwards and try to describe their correlation, similarities. So when we have a large sequence of data, then this involves how to represent their relationship here. So even for the modern transformers, their learning is basically related to using statistical principles. The only difference is those models would be too sophisticated, then we need to incorporate a massive skills and computation steps here. So this quick example just tells us how statistics could help machine learning research. On the other hand, if I'm going to turn the lens the other way, what does machine learning bring to statistical field? So here I'm going to quickly share some of my personal perspective on what machine learning would bring opportunities or challenges to our statistics here. So my first perspective concerns the reliability and risk. So if I'm going to draw a quick analogy between drug development and large language models, then we would notice we don't approve any drugs without careful, rigorous testing, right? We always document risks and side effects explicitly, and we also monitor after deployment. If there are severe problems, then there would trigger recalls. So this is a procedures in terms of drug development. On the other hand, for large language models, they also have side effects. So data quality dependence, bias and fairness issues, and safety and misuse risk. And also for large language models, they don't really build in intrinsic notion such as I don't know. They always give you output if you have some prompt. So one particular concern related to the large language models use is related to hallucinations. So large language model can produce plausible outcomes, which looks okay with confidence. But unfortunately, many of them or some of them could be factually incorrect. And hallucination rates vary from different language models and from depending on individual tasks. Sometimes it could be small, maybe a single digit rate. Sometimes it could be as high as 40 or even 50%. So in this case, what are we going to do? So if we are thinking, if we want to distinguish, when we do like a drug development or prescription of drugs, we would be very careful in a sense. We want to differentiate high risk use or low risk use. So like a prescribed medicine versus over-the-counter use, right? So in comparisons, can we do same things for the large language model use? So if it's a high risk related to healthcare or legal or policy issues, or if it's just a low risk use in terms of like grammar polishing, grammar corrections, or coding, or even brainstorming ideas, then should we distinguish the use of these two scenarios? So I would think in both cases, deciding how much to trust a model output is fundamentally a statistical question. So it requires uncertainty quantifications and risk assessment and principal validations, right? So I would advocate in this case, we shouldn't break down, we shouldn't create a boundary between two. Instead, breaking down the boundaries between statistics and machine learning is not just research priorities. It is also an educational one. My second perspective is related to changing nature of data. So modern data are quite different from traditional data in a sense they are richer in structures and could be more complex in terms of the different formats. So in this case, it would generate many new challenges here. So beyond our traditional data sets, data nowadays have more features in the following sense. In our traditional data, we, most of the time, we are dealing with numerical values. And the data could be structured, and it could be connected by design or sampling, even though we do handle observational, the data coming from observational studies. On the other hand, for modern data, many times they are just in digital forms. So they could have an image format, a text, video, or audio. So in that case, how to convert them numerically? So data representation would be important. And also, right now, in machine learning context, people started working with so-called synthetic data, which would be generated based on certain model. So when we use those kind of data, what would be the new issues? So modern data could have a high dimension, but does it mean more data would have a better inference? Maybe not. So what we can learn depends critically on how we represent our data, right? For example, transforming like a raw image or video data into meaningful numerical representation is very critical. So that would determine what our learning outcomes or whether or not our inferential results are valid. And another issue is traditional data would usually be static, which means we have data there. We have data ready, then we do data analysis, even if we have longitudinal data or time series data. But on the other hand, right now, many data would come in a time order, in a real-time sense, which means they could be dynamic, streaming, and evolving. So we may constantly update our learning and our modeling. So in this case, statistical plays a big role to talk about the quality of data in terms of collection process, representation methods. And probably we need to rethink about our traditional modeling assumptions. So integrating statistical thinking and machine learning techniques could be nice. It could give us some unified theory methods and maybe scalable computational results. So my third perspective is about changing nature of modeling itself. So if we think our traditional models just provide first order approximations to the underneath relationship among the variables of our data, then maybe for modern days, we can go one step further. We can explicitly model our data qualities in order to achieve a higher order approximations. So this basically means accommodating variabilities generated from data collection process, data pre-processing, and data representations or labeling or feature extractions would be useful and important. And as I mentioned earlier, traditionally statistics emphasize interpretabilities, but less so in machine learning context. But right now, both fields are kind of converging in a sense. For statistical fields, we pay a lot of attention right now to address data complexity, imperfections, and with a stronger emphasis on computation. And machine learning right now has a growing interest in developing interpretable machine learning procedures. So I think I don't have much time, so if I'm going to close this, I want you to have several take-home messages. First, statistics and machine learning are deeply connected, and their close interactions will define the future of trusted AI. Second, data quality is central to modern AI, and statistical thinking will play a huge role in terms of addressing those data quality issues. So with raw data, we do need to integrate modeling techniques, data quality, data representation, and computation together in order to generate meaningful inference, prediction, and learning outcomes. So if we think the 20th century was about modeling, building models, then maybe we could think 21st century may shift the emphasis toward data quality, representation, and modeling, which would be powered by machine learning. So I want to recap this well-known statement from George Box. All data, all models are wrong, but some are useful. Okay. Then I want to give a companion statement. All data are imperfect, but some are useful if properly represented. So I hope this is a key message from today's talk. So before I conclude, I want to make a quick plug about the coming book on likelihood and extensions, co-authored with Nancy Reed and Christina Varen. I hope this would be of your interest. And I also like to thank Thierry Checol, is he here, for devoting his time and expertise to prepare the French version of these slides. So I'm going to conclude my talk with a few words of thanks. First, I want to express my sincere gratitude to the Statistical Society of Canada and the awards committee for this tremendous honor. I'm very grateful for that. And definitely, I am especially grateful to Professor Nancy Reed for nominating me for this award, and also the colleagues who generously wrote letters of support. Without their efforts, I can't be here. And I have been very fortunate to learn from many wonderful mentors through different stages of my career. So here I want to remember my late PhD supervisor, Don Fraser, who was the first SSA gold medalist. So when I first encountered statistics, it was a subject I particularly disliked. I don't really like statistics at all. But it was Don who introduced me to the beauty of maximum likelihood and statistical thinking. And he was very patient with me and somehow transformed a reluctant student into someone who eventually earned a PhD degree in statistics. So I'm very grateful for that. And I have also been very privileged to work with many wonderful and talented trainees, collaborators, and colleagues. So their creativity, devotion, and friendship have greatly enhanced my research and my career. And so I'm very thankful for that. And finally, I would like to thank my family. I'm especially grateful to my husband, Wen-Chin He, who is here, who has been a long-time collaborators with me on many research projects. And people often said couples usually have endless things to talk about when they are young. But gradually, they run out of things to talk about when they get older. But I often joke, for us, maybe this will never happen, because statistics and machine learning give us countless things to talk about. So I think when I get older, I don't have to worry about to just face to the wall without being able to talk to him. So I feel incredibly fortunate to have shared my life and research with him. And also, I would like to thank our children, our son Morgan, who is here in the audience right there today, and also our daughter Joy, who is she wanted to come, but unfortunately she has to present her very first conference talk right now in New Orleans, exactly the same time. So they have taught me at least as much as I have taught to them, probably even more, because they constantly challenge me on almost everything, challenging on my views or whatever my thinking is, but not one thing, statistics. So they never challenge me on my statistics. So I think like when I watch their growing and navigating their own research journeys in graduate programs, that has given me like a renewed appreciation of the resilience and courage required of young people, young researchers right now. So as we enter the age of AI, I think our next generations of statisticians and researchers face tremendous challenge, but also extraordinary opportunities. So I look forward to many new discoveries they would bring to us in the near future. So I'll stop it here. Thank you very much.
Thank you, Grace, for this very inspiring talk. If you want to have a measure of the interest of the audience, nobody left for coffee yet. So if you have some question, maybe.
So Bruno is so nice, he didn't cut me earlier.
So maybe some questions to Grace? Comments? So if not, let's thank Grace again.